Hey there, this is Feng Chun from University of Delaware. This is a recording video for our paper Uncertainty Guided Model Generalization to Unseen Domains. Domain adaptation is a well-studied problem where we have one source domain, one target domain, and some target data is available during training. Different from domain adaptation, in domain generalization, the target domain is unseen, but we have multiple source domains. Here, we consider a worst-case scenario. What if we only have one source domain, but expect the model can generalize well to mine the unseen target domains? The problem is called single-domain generalization. To address single-domain generalization, previous works cast this problem in a worst-case scenario. Judy proposed adversarial data augmentation to generate augmented samples. Models trained on augmented samples are expected to generalize well on unseen domains. However, the domain transportation is severely limited by the worst-case constraint. MAD proposed to relax the worst-case constraint and encourage large domain transportation. However, there are two limitations of these methods. First, they ignore the uncertainty quantification when deploying the model on unseen domains. Second, they overlook the augmentation in label space. To tackle the limitations, the first challenge is how to access the uncertainty from a single source. Bayesian neural networks are commonly used to integrate uncertainty into models. However, it cannot efficiently quantify the domain uncertainty. The second challenge is how to augment the label space. Mixup pioneers label augmentation by randomly interpolating two data examples in both input and label spaces. However, Mixup can only generate in-domain augmentations. Besides, the interpolations are sampled from a fixed distribution, which largely restricts the flexibility of domain mixtures. To solve the above limitations, we propose uncertainty-guided model generalization to unseen domains. We use a backbone for data classification. We introduce an auxiliary network to quantify the domain uncertainty with respect to the backbone. We leverage the uncertainty to get augmentation in both input and label spaces. First, let's look at the input augmentation. The goal is to create domain augmentations to approximate the out-of-domain distribution. To encourage large domain transportation, we propose to learn phi-p via adversarial domain augmentation. To achieve it, we propose to learn layer-wise feature perturbations E and create H+. Here, we sample E from a multivariate Gaussian distribution, which can be used to easily access the uncertainty. We visualize the features and the embeddings. We can see that feature perturbation can effectively enlarge the domain transportation. To create a label augmentation, we propose learnable label mixup. First, we mix up the source and the augmentation to achieve in-between domain interpolations. Second, we leverage the uncertainty encoded in mu and sigma to predict learnable parameters AB of the beta distribution, which controls the direction and strength of domain interpolations. Specifically, we create soft labels white-tailed through label smoothing by a chance of tau. We visualize the density of label augmentation. We can see that a learnable label mixup can significantly increase the capacity of label space. To effectively organize domain augmentation and model training, we propose a Bayesian meta-learning framework. The training scheme consists of 3 steps in each iteration. In meta-train, we get theta star by updating the backbone on the source domain. In meta-test, we evaluate theta star on sampled domain augmentations. Finally, we meta-update the backbone and the auxiliary. After training, the backbone is expected to bound the generalization uncertainty over unseen populations. We evaluate our method on 3 modalities. We compare our method with the state-of-the-art and evaluate the uncertainty quantification. Here is a summary of our paper. Code and pre-trained models are available at this link. Thanks for watching.